I'm very happy to connect with you all, where I would be spending next 40-50 minutes on the magnetic fields in the universe. I'll be primarily discussing about the current trends in various parts of the world where people are still exploring new ideas and trying to understand new observations, all related to the magnetic fields in the universe, which will naturally also help you understand what are the scope, area scope in this area of research in astrophysics. So the reason it gets interesting, this magnetic fields, is that regardless of where you observe and at what scale and whatever scale you observe in the universe, say stars, galaxies, clusters of galaxies, you always find the magnetic field. Universe is filled with the medium commonly known as a plasma state, in which charges are free to move, and when the charges move, they produce currents and therefore the magnetic fields. It is, however, quite different from, say, we holding a wire in our rooms and producing a magnetic field. In the astrophysics, the magnetic fields are self-sustained. They produce the current and they sustain themselves by the process known as the dynamo. I'll come very slowly to all of these words, and all the keywords will be explained eventually. But this is just the motivation to why we study magnetic fields. Is first thing is because you just see them. This is in the center an image of a thin disk galaxy like our own Milky Way, where you know that there are types of galaxies like spiral galaxies, which are disk-like objects. And if you were to look at a side view, these are very large objects. And I'll come to the scale in a moment. You'll find that there is a coherent large-scale magnetic field. I hope you can see my cursor as well. Rajesh, is my cursor visible? Anybody?
Yes, it is visible.
Okay. So you can see that throughout the galaxy, like a star is like a tiny dot in this image. Star is a very tiny dot here. So if you look at the entire galaxy, you'll find that a single sort of magnetic field is pervading the entire galaxy. Natural question is, how do you build such large-scale coherence? How do you produce these large-scale magnetic fields? What are these? After all, we know that if there is a magnetic field due to currents in a wire, we know that the currents will also undergo resistance, and the current as well as the magnetic field decay in time. We know the age of the universe. Very natural question is, even if the universe is started by some magic with magnetic field, why the magnetic field is continuing to be present in the today's time, when this should have suffered the microscopic or the ohmic decay. You all know the ohmic decay. It should have decayed long time ago. Why the universe continues to produce and have a magnetic field? What are the conditions in which you can generate magnetic fields? So clearly, what you have in the universe, and you can pick your favorite part of the universe, and the story will still continue. If you like sun or a star, all you are given is a blob of plasma with continuous motions. Motion can be driven by some other mechanisms. For example, you can simply have a temperature gradient, and that could influence the plasma, and there may be motion. So origin of motion is a different question, but once there is a motion, there are these two side images you can see. This is a typical image or an example of a convection type motion. Stars have a convection motion. It's yet another unsolved problem. We do know a lot about convection, but not barely enough to be very confident about the nature of convection in astrophysical setting. when the control parameters such as the Reynolds numbers and the Rayleigh numbers, they become very large, there is no theory. And but we can observe them, and we see whenever you have a bright patch, that's where the motion is upward. Whenever you have a dark blue lane, that's where the motion is downward. You would have heard about the hexagonal Bernard cell-like convection, or when you boil your teapot, you do see these convection motions, upward rising medium and downward falling medium. So they together form a convection pattern. Those convection motions are prevalent in all sorts of objects, and that's where the energy lies. After all, if you want to generate the magnetic field, you have to obey some general energy principles. So if the much of the energy was locked in the motional energy or the kinetic energy, you have to somehow be able to convert this kinetic energy into the magnetic energy to produce the magnetic field. This process of converting the magnetic field, kinetic energy to the magnetic energy, is called the dynamo. In this case, you are not allowed to have a electric current at infinity. You can always have a magnetic field at this point. If you can also see my video or something, I'm just drawing, say, if you have a magnetic field at this point, I can just put a current around this and can have a magnetic field here, but this is not done in the astrophysics. Everything has to be self-sustained and self-produced, all within the system, without any influence from the infinity. So this is just an interesting image, that when you see an image of the drought on the Earth, this is a clay basically. This is the clay that has dried up in the summers, and this also forms a hexagonal-like pattern, just like the convection on a star. Pretty much the mechanism is very, very qualitatively similar, although the details will be very different. This may be convection driven by heating from below, whereas this may be convection by cooling from the top. Instead of heating your teapot, you could keep it on a cool surface and only allow the heat to escape from the top layer, and that might also drive convection layer. That is what is happening in this clay pot or clay on the Earth in the drought. So the general theme of the talk will be all the magnetic fields, but you must also be concerned that after all, this is very closely related to the motions in the medium. So motion and magnetic field, they go all together. So there are some interesting quotes on magnetic fields you can observe. While the universe is filled with magnetic fields, it is largely ignored in our analysis simply because it is very tough to deal with magnetic fields. There are very interesting quotes. I could quote, say, Einstein on Maxwell's equation. After all, the building blocks or the tools to understand magnetic fields are your Maxwell's equations. And what Einstein said, and these are the first examples of the field theory, the precise formulation of the time-space laws was the work of Maxwell. Imagine his feelings when the differential equations he had formulated proved to him that electromagnetic fields spread in the form of polarized waves and at the speed of light. Yeah? You know how the radiation comes to us. You know the entire physics behind it. If you simply take a magnetic field and a charged particle trapped in the magnetic field, it will be accelerated, and the charged particle spiraling around a magnetic field will produce a synchrotron radiation, which is what you observe by radio telescopes. And in fact, this is how we know, by measuring the synchrotron radiation, we know the presence of magnetic field out there in space. So too few men in the world has such an experience been vouchsafed. It took physicists some decades to grasp the full significance of Maxwell's discovery. So bold was the leap that his genius forced upon the conceptions of his fellow workers. So it is still not fully understood, in fact. It's not like we know it all, and there is a lot to discover, and there's a lot to understand about the In fact, what we will be mostly concerned with, a simplified Maxwell's equation, in fact, what is also known as pre-Maxwell's equation. That is the Maxwell's equation without the displacement current term. Because the plasma that we are mostly dealing with in the universe are non-relativistic, and therefore the relativistic corrections, such as the displacement current term, they are not very relevant for the discussion or for the production of magnetic field in the universe. Volger said on magnetic field, the larger one's ignorance, the stronger the magnetic field. And this is a famous book you might want to take a look at. As usual in astrophysics, the way out of a difficulty is to invoke the poorly understood magnetic field. One tends to ignore the field so long as one can get away with it. So it is very common practice to ignore the magnetic field in a variety of studies. So long as you can manage, you do that, despite being fully aware that it is anywhere there. There is hardly a piece in space where you don't have magnetic fields. So let's just have a quick sense of scales involved. So on the lab, you have, say, a bar magnet. You can build a bar magnet, and this will have a scale of magnetic field in this case, or you can have a current carrying this solenoid, and you can produce these magnetic field lines on the scale of, say, a meter, a few meters in your room. If you go to all the way to the Earth's scale, we know that our Earth has a magnetic field. In fact, that is how we are protected from the various cosmic rays and the hazardous radiations from the sun. We are well protected and shielded because of our magnetic field. In fact, there is no possibility of life without a magnetic field on the planet. And these magnetic fields have a massive scale compared to previous one of 10,000 kilometers. It's an order of magnitude, not exact numbers. So on the order of 10,000 kilometers, you have a single dipole like magnetic field, and any radiations coming from all the charged particles, they are trapped and going to the poles and shielding us from some bad effects. But look at the scales involved, and look at now. If you look at the entire sun, the sun has typically a scale of 1,000 megameter. Megameter is 10 to the 6 meters. So you have now 10 to the 9 meters scale of the magnetic field. And if you observe the sun as a function of time, the sun goes from a very high activity period where these white and black patches are the radially outward and radially inward magnetic fields. You see that sun goes from a very busy phase when there is a lot of magnetic activity to a phase of solar minimum when there is no magnetic activity, nearly zero, and then it comes back. This entire cycle is 11-year cycle, and sun has this cyclic magnetic field, large scale magnetic field. In fact, you can take the phi average, entire azimuthal average of the entire sun, you'll find that you have a large scale component of the magnetic field, which has a migratory character that in 11 years, it first appears on the high latitude. If you unwrap the sun and then take the phi average, you have the magnetic field as a function of latitude and time in such a space-time diagram. This tends to form a butterfly. You can see this is a butterfly. So this is famously known as a butterfly diagram, where the activity starts at high latitude, like say, if this is the equator, high latitudes are these regions. As a function of time, it goes towards the equator from both north and the south. This equator is the middle line, north and south, and from high latitudes to the low latitudes in 11 years, and the cycle repeats. It's a very wonderfully repeating cycle, periodic cycle, and we know these cycles existing for more than thousands of years, 10,000s of years, based on some recent data analysis. And it was for a long time not even known that these spots are magnetic field. In fact, I'll come in a bit to the history of these spots. These are called the sunspot. If you zoom in on one sunspot, you'll find that, again, this is like a granulation or a convection pattern, exactly like how I showed here. This is from a simulation. And this is the real observation. This is a real observation where you have a small scale granular motion. The size of that one granule is 1 megameter. Now look at the size from one granule to the size of this enormous sunspot. You can compare the size of the Earth to the sunspot. A single sunspot on the surface of the sun can be much larger than the size of the Earth. And it's a very, very intense magnetic field, much larger than you can produce on the Earth. Very, very intense magnetic field on the order of few kilogauss fields. extreme ejections of mass particles. You can see almost that if we were not shielded, all of that will be dumped, and you can imagine the scale. This is a tiny scale uh, compared to the. And after all, you can see that if you are producing a coherent field from a random turbulent motion, the question is, how do you build preferentially energy at a larger length scale? After all, you are injecting energy at a much smaller length scale, or you are trying to shred. If I take a single feed line, if you can see my hand or something. So if I take a feed line, which is this big feed line, and if I try to cut it by a scissor, so you will start to produce smaller and smaller pieces of the feed lines because you are just continuously shredding it by random motions. But still, when you observe, you are observing a coherent large-scale field. So how do you inverse cascade this to go, or how do you build energy from the small scale to the large scale? How does the energy cascade take place, going from the small scale to the large scale? So we'll come to all these questions in a bit, somewhat more mathematically. You might have learned about the Zeeman effect. If you really take the spectrum from a sunspot, you'll find that your spectral lines are clearly showing the three. You can see the Zeeman split plate line. These were the first time seen that they are indeed the magnetic fields and not some other obscuring patches on the sun. I'll come to the history in this slide. There is a great account of some literature. In fact, some controversies between Christoph Scheiner, and Galileo, who they were both contemporaries. In fact, we attribute the telescope to the Galileo, and also there is a question of who observed the sunspots, because after all, you needed a helioscope or a telescope to observe them. And if Galileo was the first to build that, most likely Galileo was the first to observe the sunspot. There's a good controversy, and if you're interested, you should read about this. In fact, there is this is the time of the debate whether it's a geocentric or a heliocentric system. Christoph Scheiner was then also a priest in a church, and they both had very opposite views about the nature of the universe, geocentric model versus the heliocentric model. But what you find very interesting and very painstaking work, and you can imagine that a single person here, sitting for nearly 15 years, observing the sun every day and carefully hand drawing whatever he saw on the sun through his helioscope. Nowadays, it is fairly straightforward that you can just download the solar image, and if there is a sunspot, you'll find that sun has a lot of dark patches. And this is the hand drawings from that were reported in 1630. And Christoph Scheiner, and if you look at the details of the drawing, for example, you focus on this one, you have a penumbra, which is a much darker patch, which is like here. This is a modern image, much darker. And then there are the somewhat brighter than this patch, which is called a penumbra. This is umbra, this is penumbra, and then this is the normal sun granulation. You can see how carefully the drawings were, that there were umbras and penumbras, and also the. So such a remarkable piece of works, very painstaking, hand drawing of the entire sun, whatever you see, done by this guy Christoph Scheiner for more than 15 years. So yeah, it's an amazing level of dedication. In fact, just by looking at these drawings, nowadays this is all a common knowledge, but imagine back in 1630, this was the first time that it was hinted that the sun has a differential rotation. That means the sun, look at the equator faster than the pole. So it's not like a solid rotation like the sun is in a differential rotation. The sunspots that were closer to the equator, they were moving ahead faster. Sunspots that were further away, they were lagging behind, and that gave the first hint that the sun is not a uniformly rotating body, but it is differentially rotating. It was the first example of astrophysical shear flow. Yeah? And that in turn turns out to be the most critical ingredient to generate the magnetic field, the shear. But back then, these were not known as magnetic features. These were, for example, Christoph Scheiner thought that these are little planets, little planets very close to the sun that are obscuring our light, that are obscuring the light along the line of sight, and therefore the region looks darker. He did not associate these black patches to something intrinsic to the sun. It's only later on when Hale observed Zeeman splitting only in 1908. Look at the year it took to go from dark patch to a magnetic field. It's only 1908 that we first saw the first evidence of astrophysical magnetic field. This is the first time that that a magnetic field was observed outside Earth. So it's truly remarkable, and you can see how long did it take. And but the scales involved were like enormous, and very strong magnetic fields on the order of few kilogauss. So if you are more interested in some controversy, very interesting controversy, plagiarism and stuff, you should perhaps read a bit about Christoph Scheiner and Galileo. They were both cutthroat enemies of each other almost. Now you can go further in scale, and you can now talk about a scale between the sun and the earth, which is larger scale. Earlier we had reached to 10 to 9 meter. Now we talk about one astronomical unit, which is close to 10 to the 11 meters. And that's the sun-earth scale. You see that there are a lot of emission from the sun, and basically a lot of these activity has a footprint in the sunspots. So it's the activity rises in the space weather. Space weather is, that's why, a very important topic, and it's a very hot topic right now. And there's a lot of scope and a lot of funding in this area of research, space weather, because one is genuinely interested in predicting the space weather. After all, you want to know, before you launch a satellite from here to here, you want to know before whether it is safe to travel right now. So you want to identify certain occurrences so that you can plan your space missions. So we are getting more and more vulnerable to the space weather, and it does bother us whether the space weather is a good weather or a bad weather. Just like you want to check your weather forecast before going out for a coffee outside. Similarly, nowadays our space explorations have increased, and therefore we are getting more and more worried about the nature of the space weather. This is a beautiful image of aurora, which you see as a result of charged particles being directed towards the pole of the Earth, and those basically producing these beautiful aurorae in the high latitudes of the Earth. But this is basically an example of the space weather where the charged particles from the sun and the cosmic rays are interacting with the Earth's magnetic field. But point for this talk is that this is very large scale magnetic field. It scales on the order of 1 astronomical unit, enormous size of magnetic fields. Now you can go out further and look at the entire galaxy. This is a galaxy like our own. It's a different galaxy, but it's a galaxy like our own. There's even a satellite galaxy to this galaxy. And if you look at an image in radio, the synchrotron radiation, you can find out that these arrowhead vectors, basically, there is no arrow because synchrotron doesn't tell you about which way it points. There's a pi ambiguity there. But nevertheless, the orientation will tell you that it's a single magnetic field or coherent magnetic field line on the scale of entire galaxy. The galaxy has a size of about 10 kiloparsec, which is, compared to the previous one, it is 10 to 11. This is now 3 into 10 to 20 meter. So it's a very enormous size, large scale magnetic field. Natural question in all these images is that how do you produce such extremely large scale magnetic field? How do you produce and how do you sustain them? After all, there is enough turbulent random motion. One of the primary effect of turbulence is to dissipate the energy. Just like when we speak, or when there is a fan switched on in our room, and any motion that you might have generated, or a wind flow, that comes to rest immediately as soon as you switch off the fan. When there is a fan, you feel the breeze on your face, you switch off, you feel that the breeze is gone immediately. Although when you work out the molecular dissipation time scale, it should take nearly a couple of days for the breeze and the wind to stop in your room once you switch off the room, because the molecular dissipation time scale in your room is very, very long. It's only the turbulence that breaks up these motions into smaller and smaller eddies and makes the dissipation very fast. So the natural question is, if the turbulence is so strong, it's a strongly turbulent system, all of these astrophysical systems are strongly turbulent, because the Reynolds number, the concept you might have already heard, or I'll briefly mention what it is. These are very high Reynolds number objects, so dissipation is also enhanced. So what is it that is compensating for it and producing, nevertheless, these large-scale magnetic fields? After all, it's a process now. You must seek a process which is an inverse cascade process, because energy you are injecting always at a smaller length scale. Because energy injection scale can be, say, on this width of the spiral, some supernovae fluctuations. Each time a supernovae goes off in the galaxy, it is adding a forcing and a motion in the galaxy. That scale is not very large. That scale is, say, just this much here. Yeah, some 100 parsec to 500 parsec. That is the typical scale. Galaxy has 10 kiloparsec scale, 20 kiloparsec scale. So how does this energy go from the small scale to the large length scale? Nevertheless, you anyway observe this, and we have some, but not a full understanding of what causes these. So this is a very active area of research. You can actually go even further. This is a galaxy. Now you can go to a group of galaxies, which is called a galaxy cluster. It's an image from Virgo cluster. The typical size is 1 megaparsec. That was a 10 kiloparsec. Megaparsec is 10 to the 6 parsec. Parsec is 3.26 light year. And you can see the scale in meters is 3 into 10 to 20 meters. And you observe these arrows, which are all basically the measurements magnetic field lines. And each object, each dot here, basically, these are all galaxies. These are a group of galaxies in a galaxy cluster. These are groups of galaxies. So you can see the enormous size. In fact, now there are recent images, you can go even further. You find magnetic fields even in the voids. When there are no objects, even there you find the magnetic fields. It's very, very surprising. How do you go about thinking about this very large scale magnetic fields pretty much anywhere in the universe? Whichever part of the universe you go, you always find the magnetic field. How do we understand this? So for that, I'll just, to lighten the mood also, I'll just quote, perhaps which is even more relevant today, is that there are children playing in the streets who could solve some of my top problems in physics because they have modes of sensory perception that I lost long ago. This is a quote from Robert Oppenheimer, and you know, and you can see what he's basically referring to. So our prejudices and very mechanistic approach to doing science is our own hurdle in making some serious progress. So there is a question I see that how does voice sustain magnetic fields? I'll come to some of these questions, and these are pretty much an outstanding problems. We have some understanding of these though. But first let me, this is a somewhat busy slide, and let's not look at all of this. Let's focus only on this panel. Yeah? It's only if you are more interested, and if there was time, I could have gone into this, but forget about them. Just look at here, in this corner. Yeah? This is like thousands of stars. Each dot here is a thousands of stars, where in this paper, you can go read, it's a very interesting paper, something like an X-ray luminosity is plotted as a function of Rossby number. Rossby number is like inverse rotation rate. So this side stars are slowly rotating. This side stars are rapidly rotating, okay? And you find that as the rotation increases, the X-ray luminosity from those stars increases. And then there is a saturation. There is always some sort of a saturation. Nonlinearity is one way that it leads to some saturation. So it's not that it is understood, but the point is very different kinds of star. They all lie on the, or they should be able, they are perhaps having the magnetic field properties which are very much like alike. So this motivates for having a unified model of magnetic fields in a variety of stars. These are, for example, fully convective stars. These are some like normal stars. Sun lies somewhere here. Okay. You can see how does the rotation couple with the X-ray, and where does the magnetic field come from in this plot. Yeah. So X-ray is produced by something known as, say, primarily in these stars by magnetic reconnection. So more the magnetic field, more reconnection, therefore more X-ray luminosity. So that is how you infer indirectly the magnetic fields. Faster the star, now we have enough evidence that faster the star, somewhat stronger is the dynamo, stronger the field productions, and therefore it is expected to have larger number of reconnections and therefore larger X-ray luminosities. So there are many attempts. You can see that these are not very old papers, and there is enough continuing research. In fact, we tried to understand this in some recent model this year, trying to understand the shapes of these curves to see if we can build a unified theory of magnetic field generation in the star. Why am I all the time saying generation? Because if you don't generate, it will decay, and the decay time scale will be much shorter than the age of the star. That means when you observe the star now, you will not find a magnetic field. After all, it has an age which is much longer than the decay time scale. So there must be something that must be maintaining it, and that something is a dynamo. So let's understand it in terms of a dynamo. So if you ignore your displacement current term in the Maxwell's equation, appeal to the Ohm's law. Ohm's law, you know, is J, current is sigma times electric field E, sigma is your conductivity. You will find this equation very easily. It's a partial differential equation, first order derivative. So magnetic field will evolve according to this equation, and you can pretty much say that this is the term which can produce the magnetic field, meaning del B by del T could increase as a function of time because of this flow term. So flow can produce a magnetic field, and this flow is a flow in the plasma of your system. And eta is a decay term. It's an ohmic resistivity term. So you know that if you did not have this term, del B by del T is eta Laplacian B. It's a diffusion equation. Just like you can heat a rod and wait, and then the temperature will decay. Just like that, it's a diffusion equation, heat diffusion equation without this term. So this is the term that can enhance the field, and this is the term that can decay the field. The competition between the two will decide whether the field will grow or not. This is a non-relativistic limit of Maxwell's equation, and plasma is usually modeled as a single fluid. I will not have actually much time to get into the definitions of single fluid and double fluid. All that is meant here is that the electrons and protons, or the negative and positive charges, are well mixed, and you are in a continuum limit of the medium in which your smallest unit cell has large number of particles, so much that the overall net charge of that smallest unit parcel of your medium is charge neutral. Okay, there are as many plus charges as there are negative charges, so that there is no net charge, because plasma is anyway highly conducting. So even if you create a charge imbalance, this gets damped in a very short time scale. We are anyway interested in slow dynamics and larger length scales, larger than this typically this unit scales, which are very tiny. After all, we are interested in large scale phenomena. So we can have a model which is a single fluid or continuum models, not the particle models. So we are no more tracking a single individual charges, because that will involve a different level of theory, and that is perhaps not so relevant. You want to have a simplified model to attack the problem which is as large scale as I just showed. After all, you can count the number of particles, and if you were to write those many equations for each particle, this is a job you cannot really do, even with the best of the computers possible. Here, you can ask the question, why do we only talk about the magnetic fields in the universe? After all, they're very intimately related to the electric field. The question is, any electric field, if you create, will be shorted out. You can short out the electric field because there are monopoles or monocharges, plus and minus. There is no such thing for the magnetic field. So magnetic field, once produced, it will never be shorted out. And therefore, in a highly conducting plasma, you typically don't have an electric field, because if you have an electric field and a charge separation, the charges will move because of the electric field and will just kill the electric field. Whereas the magnetic field will not be able to short out. So don't read too much into this. It's only to say that there is a Lorentz force due to the fields onto the plasma, which is largely ignored in the kinematic discussions on the evolution of the magnetic field. You can simply imagine that this velocity field is given, and for a given velocity field, you ask the question, how does my magnetic field evolve? But naturally, you know Newton's third law and everything like Lorentz force, that if there is a magnetic field, it will also push back on the flow and it will modify the flow. So you must solve the whole magnetohydrodynamics, in which you solve for the equation like del V by del T instead of only the del B by del T. And that entire set of equation is called MHD. Okay? But in a kinematic discussion like this, kinematic means that the back reaction of the magnetic field on the plasma is ignored. There are some interesting limits to this. If you take eta going to 0 in adduction equation, this leads to flux freezing, which means if you move the plasma, the magnetic field moves with it. It's a very interesting consequence. You can think about it. And that means you can twist the plasma in any random way, in any arbitrary way. Magnetic field is tightly coupled with the plasma. So wherever the plasma and the medium will go, the magnetic field will be frozen to the plasma. It will also be twisted and with them. So that is the limit in which when there is no dissipation at all. Clearly, if your V is 0 in this equation, it's a diffusion equation. So there is only ohmic decay of the magnetic field. Another interesting thing is that it's a homogeneous equation. So B equals 0 is a valid solution of the induction equation. It has a profound consequence that if the universe or any part of the universe is started with a 0 magnetic field, this equation will not be able to evolve that at all. That means the field will remain 0 for all times. What does it mean is that every system must have a seed field to begin with. Only when there is a finite non-zero seed field, this equation can produce the magnetic field or generate it. Otherwise, this equation is of no use. So there are corrections to these equations, which I will not go. Those are the issues concerning the seed field generation, which is a very interesting problem in itself. In fact, that is the main reason for the fields that you produce in the voids. After all, even in the pre-inflationary or inflationary phase, when your MHD perhaps is not even valid, you have to confront with the problem of magnetogenesis, and that could produce the magnetic field as a tiny quantum fluctuation somewhere everywhere in the space right after the Big Bang. And then after inflation, the scales became larger, and that must have the magnetic field that is filled in the void. So that could be one possibility, but this is not very well understood. In fact, the void magnetic fields that are observed today are far too strong to be explained by any current models. They are some of just too strong magnetic fields in the voids. And by strong, I mean there, you'll be astonished that it is on the order of, say, 10 to minus 36, 10 to minus 20. These are the orders of Gauss. So formally, you define dynamo action as conversion of kinetic energy into magnetic energy without any electric current involved. So the flow may act as a dynamo. So the reason that you see magnetic fields in all these objects, one emerging or one somewhat like a general consensus in the field is that these magnetic fields are all produced by a dynamo process, but the dynamo might be different type of dynamo for different types of objects. Okay. In galaxies particularly, there is something known as an alpha effect, which is perhaps most important one. In fact, alpha effect is most important for even the stars. So I'll briefly describe or I'll give one example of how do you understand and how do you produce an effect which could generate the magnetic field. How does one understand? Given there are so many wide range of scales involved, yeah. For the sun, you can imagine that the scales, we may be wondering about the energy, kinetic energy at 1 megameter and the magnetic field at 1000 megameters, so 1000 times larger. So there is such a disparate scale involved. how do you really understand? So then there is a technique which is known as a model, which is known as a mean field model to understand the turbulent dynamo. Why turbulent dynamo? Because the motion that you are given is a turbulent motion, a random motion. It's a different problem, and it will be a different lecture if one were to discuss the evolution of those turbulent velocity fields that is governed basically by the Navier-Stokes equation. But I will not have any time to get into that. So let's only focus on the evolution of magnetic field. What one typically does is that you split the total magnetic field B prime into something like a mean plus fluctuation. So if I apply some kind of an average, you can consider an ensemble average. If you take an ensemble average over the small b, that will vanish. Ensemble average similarly over a small v will also vanish. And whatever is left out is actually your mean flow or mean field. Okay. So similar, so then you can just take this equation, apply your averaging, Reynolds averaging. You must obey some averaging rules. There are averaging rules. For example, average of an average is an average, is the same average. Okay, it's not a very obvious thing, but there is a set of rules to be followed, which are called the Reynolds rule. I will again not get into the Reynolds rule. I only want to give you a flavor of what you do. Is that you take this equation, you average. Average is more like filtering. What some people describe is filtering is actually if you have glasses. Yeah. So if you have glasses, if you can see me. So when you take off your glass, you have actually filtered. No? You can't see things very clearly. So there is already some sort of filtering. You increase your resolution simply by putting on the glasses. Filtering is a process like that. You want to smooth your data, you want to smooth your equations. But Reynolds averaging has to obey certain specific rules, only then they qualify to be a good averaging in a sense. So once you average that previous equation, which is an induction equation, you find that the evolution of the mean field, maybe for the sake of this discussion, for capital V. Suppose I declare that there is no mean motion in the medium. Although for galaxy or for the star, the rotation you can include in the mean rotation, mean flow, right? So there is a mean flow. But more interesting is the term which is highlighted as green here, is the EMF, which is called a turbulent mean EMF. Yeah? So you see all the big capital quantities B, except this, are all made up of pieces which are all capital, meaning mean is driven by mean, but this quantity is solely driven by the fluctuating quantities. So that means if I take this angle, which is average, over this velocity alone, you get 0. If you take average over B alone, it is 0. But if you take a cross product and then take the average, or a 2-point function here between the two, you get non-zero value. So these quantities have individually varying over scales which are much small, but they can have correlations that can exist for scales much larger than their individual scales. In those cases, you might be able to produce a large scale magnetic field. So it's already a hint that you can see that by having a motion and small fields at very small scale, you in principle can drive a large scale dynamo. Okay? The inverse cascade is implicitly, it's already visible in these equations. But the source for this del B by del T is this E, and source for this is a small b. So, but this we don't know. So then what you do, you take the total equation and you subtract this to obtain an equation for the fluctuating field equation. What you will find interestingly is that, please appreciate the problem here, that you are trying to determine the evolution of capital B, which involves E. For that, you must solve for small b fluctuations. Nevertheless, you can make certain approximations, and I'll not get into the too much detail. If you're interested, you can read about first order smoothing approximation. It's a closure model. You can very quickly close these equations. After all, you want to write B in terms of E, then you expand E in terms of capital B itself, and you have these prefactors which are transport coefficients. These alpha and eta t are your turbulent transport coefficients, which govern the evolution of large-scale magnetic field. It is basically these quantities which are made up entirely of the small-scale velocity field. This is where the motion comes in. So motion in terms of v dot curl v, you can try to imagine this is a very interesting motion. V dot curl v, if this is non-zero, it gives you an alpha effect, and v dot v is like your kinetic energy density. Kinetic energy density gives you turbulent diffusion, comes with a minus sign here. When you plug it in, it will give you plus eta t square. It will just augment this term, eta t square here it will be. And that will lead to faster and faster decay. So this is the effect that is commonly known, that turbulence leads to dissipation, but this is the term which can overcome that. It's also solely made up of the turbulent quantity, small scale motion. So you can see that granulation or the convection or the supernovae driving in your galaxy, they can all basically contribute to this small velocity field. So as far as this talk is concerned, you replace the galaxy or the sun, the motion there is simply this object here. This small v is essentially like a supernova. Yeah. But what it gives you is interesting enough, that alpha, and when this is finite, I mean, it's not guaranteed that this is finite in every system. Oh, so I see that I have already taken 50 minutes and I have not even come to the most interesting part of the talk. So can Rajesh or somebody tell me how much time or... Huh?
Yeah, it is. We have planned it for till 3, I guess.
Okay, so can I steal another 10 minutes or so?
Oh yeah, yes.
Okay, so
yes,
sorry
yes,
for this. I am actually going so slow, but maybe I'll speed up eventually. But please give me 10 extra minutes, and then I'll make it even more visible. So this alpha is present, and this quantity, which is helicity, called helicity, v dot curl of v, it's a pseudo-scalar, which means it does not transform in a mirror image just like a true vector. It's a pseudo-scalar. It changes sign. It is a true vector, but this quantity helicity is not a true vector. Okay, you can think about, say, rotation and stuff. So, but think about what is this pseudo-scalar. Magnetic field, on the other hand, also is a pseudo-vector. So you have to somehow break the symmetry of turbulence. Turbulence is made up of velocity field. Pure velocity is true, but magnetic field is a pseudo. Somehow you break the turbulence of the velocity field. It's a topological argument in order to produce the magnetic field. Mathematically, one could say that, after all, you are going to produce a pseudo vector. So turbulence must break its symmetry somehow. So that's why whenever there is a kinetic helicity, it's under that you can produce a magnetic field. Systems that have rotation and stratification, which is very, very common to pretty much all the astrophysical objects, they are rotating and they are stratified. There is a density stratification. You can think of galaxy or a sun, its convection zone. All objects have rotation, differential rotation even, and stratification. It is enough to give you an alpha effect. Okay, and the motion you can imagine is a screw-like motion. It's a spiral-like motion, and spirals or the screw-like motions have a handedness. It's left-handed or a right-handed. So if you see a left-handed screw in a mirror, it becomes left-handed. Left-handed becomes right-handed, so it changes under mirror symmetry. So it does not have mirror symmetry. So it's very, very important. So then that term, I'm simply saying that you put it here and solve, you might find a dynamo. So this is the term that is commonly known as an alpha effect producing the large scale magnetic field. General scheme is given here. Large scale meaning a lot of these things are produced by that. So there is general rotation, and if you look at in the vertical, like in this plane, there is a strong density decrease. This is the direction across the plane. Okay, I'll very quickly go to another quantity called magnetic helicity, and don't read any of this. This is a quantity which is constructed from the magnetic field. It's a vector potential A. It's a topological invariant. After all, there must be some very strong constraints on the magnetic field if there is an invariant quantities. So this quantity turns out to be invariant. The resistivity, the ohmic resistivity of the plasma in astrophysical systems is nearly zero. So dH by dt does not evolve much. It's nearly constant. if that is constant, what happens, and if you can really see my screen here, or if you can see me, if my video is seen to you, all I'm saying is that I can produce a small scale motion in this wire by this action here, and eventually you find that the wire turns and makes a large scale twist. Okay, large scale twist. So you can see that the inverse cascade is actually a process of energy minimization. If you write spectrally at each k, the energy, magnetic energy goes as small k. K is a wave number. Wave number is 1 over the length. So k times hk, and if h is conserved, you minimize energy by going to smaller and smaller k or larger and larger length scale. So you can also view this inverse cascade as a process of energy minimization, relaxation process. So if the field is configured in such a way that the much of the magnetic field or magnetic energy resides in a large length scale, this is energetically more favorable, stable condition for a star or an object. So this is one way to think. Naturally, because large scale field has one helicity, but the helicity is a conserved quantity, but a signed quantity, there must be internal twists, and the fields thus produced must always be bihelical. That means at one length scale, the sign of helicity is plus, then other scale must be negative. So that net helicity is not produced, or it's zero. Now we come quickly to another aspects of the sun, and this is an example here that you please think about difference between the waves and modes. Modes are basically like the standing eigenmodes in your organ pipes. This is an image which you clearly see if you go to the church. You can see very beautiful organ pipes, yeah. And I have many images of organ pipes from various churches, and you can see that just by studying by making some tuning fork experiments in these organ pipes, you can actually measure the speed of sound in the air. You can measure that, right? Tuning fork experiment, if you recall. Like, after all, the wave is trapped in a cavity. So these form a cavity like your musical instruments like guitar or the tabla or something. Sun is exactly similar in this context like a guitar or a tabla. Okay, sun is a musical instrument as far as the waves and modes are concerned, considered. You excite a part of the sun and the wave travels and it bounces off. There is a cavity from below and cavity from above, and this forms modes, standing eigenmode, just like in the cavity in the organ pipe. Okay, this is interesting that there are about 250,000 out of 10 million expected modes have been identified. This one image is one realization or one of so many 10 million expected modes. Red meaning red shift, blue meaning blue shift. So entire sun, it's a global oscillation of a star. A study called Helioseismology. It's a global oscillation of the star. The entire sun is oscillating with this sort of a mode, where this part of the sun goes away from you, this part of the sun comes towards you. So you can imagine this very complicated guitar-like structure, very complicated structure. And this is exactly having like a music, like you have in the music. There are various kinds of modes, P meaning the sound modes, and then there is a one mode which is the mode. I will not discuss many other modes. In fact, this also will take a long time to describe it in detail. This is essentially your dispersion relation. You know that your frequency and the k, omega k relation are known as dispersion relation. This is in solar context, L nu diagram. L is like k, this is like nu. So, but you think of the surface of the sun, and now think of the ocean. When you go to say the seaside, you have a lot of sea waves, right? These sea waves are basically called the F mode or the fundamental modes of oscillation, and they can teach you a lot about the star. So the goal of helioseismology is by measuring these sound speeds which are traveling inside the sun, you can study and infer the interior properties of the star or the sun. See, the sun is opaque beyond its photosphere. So how do we know what is inside the sun and the properties of the star? The properties of the star is known by actually the helioseismology, in which you study carefully these oscillation patterns which are visible on the surface of the sun, which are actually traveling deep inside, when these waves travel inside, they carry useful information, and you can infer some of these. This is the study called helioseismology. Science is studying the wave oscillations on the sun. Goal is to determine the physical conditions in the solar interior. Remember, we are very much interested in predicting the space weather. By that, one really wants that even before there is some emergence of the sunspot, we want to know beforehand so that we can predict our space weather. Yeah? If you know already before that the sunspot is going to emerge, you can make preparations. You can see that, okay, once this emerges, there will be a lot of interesting things, charged particles, dangerous things will happen. So you want to predict this phenomena. Okay, the way to predict is by studying the F mode or the fundamental mode, which is what we have done in some recent times. It's a very outstanding topic, and we are very much active. A lot of people are very active in studying. What you have to actually study is look at the velocity oscillations, velocity fields that are measured from the surface of the sun. That's the only data you have. So let's skip through the simulations. These are the simulations. I will only discuss the observations. Okay, but the reason we studied those observations were based on our simulations, that if you consider a star, a small segment of a star, in which this is the depth of the star, 0 is the surface of the star, above 0 is the atmosphere of the star, these are the interior, and we can bury or we can put the magnetic field lines below the surface before they have emerged, and we try to look at the imprints of these magnetic fields on the fundamental mode. What we found that F mode shows some sort of a strengthening before there is an emergence. So we could actually predict before the sunspots appear, we could predict by looking at the F modes of the star. F mode is exactly identical in dispersion relation to the ocean wave. The dispersion relation is omega square is G, okay, I may not have written it, but you can write omega square, which is the frequency of oscillation square, is equal to G, which is the surface gravity of the star, times the horizontal wave number, the K determined on the in the surface plane, yeah, on the Earth. And you can carefully go and check the ocean waves and measure these. You will find omega square turns out to be G times K. Yeah, that's the frequency or dispersion relation of the F mode. It has identical dispersion relation on the sun or any other star. So by measuring this, you measure the surface gravity, but magnetic field changes the dispersion entirely. Okay, so if this was, so this is a parabola, right? Omega square equals G times K. So omega is square root of G times K. That is a parabola, right? So if you focus only on these ridges or modes, this is a dispersion relation. These are the sound waves, exactly the sound waves of the kind that we are speaking right now. They will appear in such dispersion diagram like this. But for the surface mode, which is only lying on the surface of the star, it's independent of whether it's a planet, star, or something. It's a classical, which is non-magnetic. This is how it looks, ridge. When you put some magnetic field, it changes to something. This is a dispersion relation dashed line predicted by Chandrasekhar in his book, if you're interested. But when there is a non-uniform magnetic field, this is not studied yet in a theoretical fashion. Only simulations exist. This is the simulation that we did some time ago. You can see that the same field or the same dispersion changes to something so dramatic that this is no more a single valued or single frequency. The line width of this F mode has increased by many orders, by many fold. Yeah, it's very, very broad line. So we thought that we can perhaps try to see if before the magnetic field has emerged on the surface, if you look at the vertical cross section, you'll find that this is the surface, this is the atmosphere again, this is the depth of the star. Before there is an emergence of the magnetic field, we found that the F mode, if you measure the strength of the F mode, it is larger compared to the corresponding hydro part or the non-magnetic case. So there is always some gap here. And that gap is what we were after to determine the properties of magnetic field before their emergence on the sun, because that is intimately connected with your space weather. So there were enough motivations to study, and you can see that we are not doing anything except taking a data from a satellite, the data we took from this satellite here, SDO, Solar Dynamics Observatory, and the imager is helioseismic and magnetic imager. This is our Earth. Lots of satellites. You can see that we have to know the space weather also to protect our satellites. There are so many satellites. Actually, the space is a very busy place. There is nearly a traffic jam. So you can see there are so many. And there are motions on the surface of the sun. This is basically line of sight velocity component of the sun, which you can measure by looking at a particular spectral line, and whether it is blue shifted or a red shifted compared to its rest frame frequency, you can see whether that part of the sun is going away from you or coming towards you. So that's a typical line of sight velocity Dopplergram that you can measure from such an instrument. Simply that is needed because based on that velocity field, which you could suppose measure from the surface of the star, in this cartoon, say this bold line here, this will be a function of, say, horizontal coordinate x and time. If you Fourier transform, that will become k and omega. You take its power spectrum, that will tell you various properties of all the omega ridges and stuff. After all, here what you are plotting is a contour diagram of the power spectrum, which is nothing but mod velocity square after taking its Fourier transform. That's all. Okay, so that tells you a lot about the oscillations of the star. Now we look at the quiet sun. So this is the sun, real image of the solar magnetic field of the sun in the year 2010, and we try to track it for say 10 days. And this is the central meridian here, central meridian passage here. So you go from west to east and track two patches, one north and one south. So red is north, blue is south. For the F mode, which has very simple dispersion relation, omega square is g times k, you don't expect that the F mode is different in the north and in the south. You expect that the F mode property, the observable you can construct is F mode energy. So whatever you need, it doesn't matter. Some property of the F mode or strength of the F mode. In the north and the south, there is a lot of fluctuation. After all, sun is a very, very complicated object. There's a fluctuation. And 0 is the time of central meridian passage. When the patch reaches the central meridian here, you go from here to here. So 0 is the central meridian passage. You find that it's nearly flat. And red and blue they don't have any systematic difference between the two. So F mode you conclude is symmetrically distributed in the quiet phase. Now you look at the active phase when there is an active region here. So look at this active region, which emerged in isolation. 0 is the time here in this entire plot. If you look at the 0 is the time when this active region emerged. Shaded region is the evolution of the magnetic field. It's a real data. So 0 is the time when it was given some number. It was identified as some good active region, which is anyway going to flare. It will produce a lot of solar flares. Maybe some coronal mass ejections are also coming from such active regions. So 2 days, if you backtrack this same patch 2 days before, because the sun is rotating, 2 days before this patch would go here. T active region minus 2 days. So at a time which is 2 days before this emergence, so 29th of November 2010, on 27th of November, the same patch will be here, and there is no magnetic field. Now you want to see what happens to the F mode, which you are measuring only from the Dopplergram or the velocity field. You have no access to the magnetic field there, because there is no magnetic field here. You see, gray is like 0. Oh, I already want to, I think I'm very nearly close to finishing. This is my, I think, very last slide. So you can see that 0 is when you identify this an active region about 2 days before. Forget about the middle panel entirely. This is not of use for now. The F mode energy, it looks first of all the evolution in the target patch, which is the active patch, and the blue is the control patch. They look very different from the quiet phase to the active phase. This separation is what we could measure. We say that even before there is any emergence, there is a peak in the F mode energy. F mode is measuring You are measuring exactly how you are observing your ocean and the surface waves, right? So you can see how powerful these techniques could be, that you measure the motions on the surface of the star, and you are already going to predict 2 days before you have seen this peak, you are going to say, on this patch, there is something going to emerge, and 2 days later, there is something emerge. So there is enough preparation time you get. So an active region breaks the symmetry of the F mode. This is an ongoing work. There is a lot of controversy in this. We are still investigating many more examples of this. If you're more interested, you can read this paper. But we are only trying to say is that just by looking at magnetic fields, there is so much we learn about even the oscillations, as simple as things like oscillation. So I'll conclude. So conclusion, maybe you can skip, because anyway, this is critical to better understand turbulent convection. The reason I say is that we still don't really know if all these theories which demand an alpha effect, how much alpha effect is there in each different system is something that we don't know. Convection is a fundamental property in all of these systems. We really don't have a full understanding of convection, and therefore, perhaps we don't really fully understand the magnetic field. So there is a large scope. There is enough scope to continue to think and worry about the generation, production, maintenance of the magnetic field. But I think I have given you enough flavor and motivation to look for or continuing to think about the magnetic fields, which you observe in no matter where and at whatever length scale and time scale. Length scale and time scales are intimately connected. So in all cases, you find fields, and there is, and we have yet to understand quite many associated phenomena. I gave you an application of this in terms of magnetohelioseismology. Just by looking at the oscillations on the star, we were sort of successful in predicting that there was a magnetic field and that it could be predicted well in advance. So there is enough interest in this field. And if you are more interested to know more about any of these, so this was an example from the sun. I started from something like Galaxy, and you can fill the gap, accretion disk or something. In all these cases, perhaps there is a different mechanism operating, but the underlying generic mechanism is that you are using the motion to produce the magnetic field, and how you order them will depend on the exact mechanisms involved and the system that you are studying. So thank you very much, and I'll be happy to discuss more.
Yeah, thank you, Nishant. So, large number of audience from student critique. So I hope by this time they know how theories are not such a non-trivial thing and such a serious thing. So if there are any questions, so please ask.
Good afternoon, sir. My name is Kumar.
Yes.
My question is how does the voids around the galaxies sustain magnetic field?
Yes, it's a very good question. So one possibility is that given the voids do not have enough or expected to not have much turbulent motion, it is possible that any trace of primordial magnetic field that could be produced in the inflationary phase because of some processes such as magnetogenesis, they have not decayed in the galaxy voids. So the decay rate is also very, very small. For example, for galaxy, if you work out a decay time scale based on ohmic time scale, ohmic resistivity of the galaxy, you will find that this is much larger than the age of the universe. So that was an early argument that why do you need a dynamo? Because the galaxy once has a magnetic field, it will never decay in the lifetime of the universe. The argument is poorly constructed because the turbulence changes the picture and the decay time scale becomes very, very small. In case of void, it's not very clear if the decay time scale is significantly reduced, in which case any trace of seed magnetic field that could be produced in a very early phase of the universe, just after Big Bang, those fields might be still present in the voids. The surprising part is that the void magnetic fields are measured currently to be very, very strong. And the limits that we are seeing now is that it is so strong that we need some completely new mechanism to explain already in the time of the inflationary time, in the magnetogenesis time. So what is it that can produce, first of all? So there is one very interesting idea that has come, which will be relevant in the early universe. It's a chiral magnetic field effect. In the induction equation, when you have asymmetry in your right-handed and left-handed leptons in the very early phase of the universe, that produces an additional current or additional effect in the induction equation, or your Maxwell's equations get modified. It's a very early universe time. That can give you an additional source of magnetic field, which is perhaps only in the very early phase, and possibly that gave you a helical magnetic field, which is observed that if you have a non-helical magnetic field and a helical magnetic field, the decay of helical magnetic field is much slower. So if you are lucky that there is a chiral field present in the early on, and if the field is helical, it will decay even more slowly than the normal magnetic fields, then perhaps that could explain the wide magnetic field. But as of now, this is clearly an outstanding topic.
Thank you, sir.
Yeah, if anyone.
Sir,
Yes.
Yes.
sir, does a magnetic field other than sun directly affect us?
Can you repeat? Sorry. Can you
Sir,
repeat, please?
does a magnetic field other than that of sun directly affect us?
Definitely, I think. I mean, affect in the sense, you see, when you observe pulsars or any radiation, I don't know what you really mean by affecting. Affect, if you mean hazardous effects, then of course sun affects us most because it is close by, and therefore the flux is very much, and that could potentially be very harmful. And the flux becomes, that is 1 over r square, so the fluxes are very, very tiny for any other astrophysical objects. In that sense, you are safe. But of course, you want to be affected by the magnetic fields of other objects. When you are observing pulsars, there is no pulsar without a magnetic field. And the observations you are making from your Earth-based observatories, the radio telescopes, say in Bangalore and even GMRT in Pune. So these are routinely measuring pulsars, which are essentially affected by the radiation coming due to magnetic field of those very distant objects.
Thank you, sir. So I have one more doubt. So what
Yes.
are called seed magnetic field?
So seed magnetic field is, first of all, a necessary ingredient for the induction equation. You need seed magnetic field. Now, seed is something that a magnetic field can be produced from vacuum, for example. That you start with a zero magnetic field and something must produce a magnetic field. For something on the earth, perhaps it's not such a great deal. You can take a wire and you simply pass a current and you'll say that I produce a magnetic field from zero. So there was no magnetic field at time t equals 0. Think of an inhomogeneous differential equation. Inhomogeneous differential equation is like a source. You have a source term. So this Biermann battery term, even when you have a B equals 0, can produce you a finite magnetic field because of these misalignments in the pressure and density isocontours. But as time passes, the misalignment will go to 0. That means this term will go to 0 and you get usual induction equation. But once you have produced the magnetic field, it is very, very hard to get rid of it. And that has already given you the seed field. So the story goes as that at some point in the universe, very early on, you had this Biermann battery term that gave you the seed field, which were then further evolved by the rest of the induction equation, which I discussed today.
Yeah. So, is there any other question?
Hello.
Yes.
Yes,
Hello.
yes, yes,
Good afternoon,
Yes. Yes.
sir. Sir, I am
yes,
Rajesh. I have a small doubt.
yes. Please go on.
Sir, sir, studying more about these topics will actually through torchlight the unseen picture of the universe. Yes, sir. But more than making these theoretical formulations and also increasing our understanding on the universe, can we make any practical application out of this knowledge that we attained?
Um, most people study it just for the study's sake. There is a lot of practical knowledge. You can learn various concepts from these studies. In fact, now that you ask, and that makes me think, even today, people are making dynamos in the lab, laboratory dynamos. In fact, the person who built the first lab dynamo is still alive, called Galaxies. And he built this first dynamo experiment in the Riga. It's a small country called Latvia. And by that, you can see that there is enough interest to have a plasma confinement. For the plasma confinement, you need different types of perhaps magnetic fields. You want to continuously study that to perhaps at some point later in life to completely replace your energy generation process. You don't want to burn coal. You want to go green. You don't want to rely on, say, this nuclear reactors and stuff. So fusion is perhaps one way, but that requires plasma confinement. And a lot of ideas that you learn in these astrophysical magnetic fields, they come very handy and they become very useful in actually applying those to some laboratory conditions. But most people are interested to study just for basically understanding the universe more and more, refining our understanding. Not necessarily worried much about the application part, but definitely the equations that you derive, they are generic equations. And if some understanding emerged, you could use it. One possible application could be in the energy generation, I can imagine.
Thank you, sir.
Yeah. So, if there is no other question, we can conclude. So, I think if you, yeah, yes, yes. If there is any question, you can ask. Yes.
Uh, okay. Sir, is there any connection between astrophysical jets and magnetic field? Or what is the connection between them?
So there is a great connections. In fact, one might argue and say that if there was no magnetic field, there would not be any jet. So jets are basically like confined. It's like very confined jet like basically jets. And the confinement magnetic field. One thing that it does is that it confines the plasma very much because the charged particles are not arbitrarily moving anywhere. So they are confined in space, and that confinement can give you jet-like geometry. So basically, by jet, you are tracing the magnetic field there. Jet magnetic field is the one that is basically even leading to the jet in a sense. Yeah, and the question then becomes that how do you produce those magnetic fields which can be so jet friendly in a sense? Yeah, so they are very intimately connected.
So, yeah. Is there any other question? Yeah, I think there are no more questions. Yeah. So, if you haven't noticed, most of the ideas from the forenoon sessions talk is directly applicable to magnetic fields. So, anyway, I thank Dr. Nishant for this wonderful talk, and I also thank our participants for uh, attending our program. So, thank you, everybody. Thank you.
Thank you. It was a good experience, and yeah, wish you a good day. Thanks.
Thank you. Yeah, thanks.
So shall I disconnect, Rajesh, or what do you
Yeah,
say?
yes, yes. You can. You can disconnect. You can disconnect. Yes, yes.
Oh.